All right. Welcome, everyone. My name's Janine Burke-Wells. I'm the Executive Director of VIBRA, and thanks for joining us for another installment of our Lunch and Learn webinar series. Although, once again, we have a lot of folks joining us from the West Coast, so enjoy your breakfast there. A few housekeeping items. Please put your phones on mute. I may try unmuting everyone at the end for questions and answers, but I'm going to ask you to use the chat function, which is right here, to type in your questions, and we will get to those at the end of the presentation. This session is being recorded, and the link to the recording will be shared with everyone after the webinar. So thanks again for joining us today. We're going to learn about an innovative solids treatment method that deals with PFAS. And our presenter today is Doug Hatler with 374 Water, Inc. And before I forget, I want to thank 374 Water for sponsoring this event so we could offer it free to our members, as well as members of our sister Biosolids organizations across the country. Doug is joined by a few folks, and I'll let you introduce those folks. Doug serves as 374 Water. He serves them in a business development capacity. He has over 30 years of experience as an environmental engineer, environmental regulatory specialist, sales and marketing executive, and EHS and sustainability management consulting. He earned a BS Environmental Science as well as an MBA from Rutgers University, and he has a master's degree in environmental engineering from the New Jersey Institute of Technology. He's going to talk to us about the development of a system that effectively treats PFAS-contaminated sludge and biosolids, and you'll hear all about the process and the technology. And 374 Water came to our attention after a presentation to the Water Research Foundation's LIFT program. So I'm going to pass this over to Doug, who is viewer 10. And here we go.
Okay, everyone
so
see.
Enjoy, everyone.
Janine, can you see the slide?
Yes, very good.
Great. So thank you all for being here. Good day. It's Friday, and we've got the weekend coming. So my name is Doug Hatler, and I'm representing 374 Water. On the call, I'm also pleased to introduce Kobe Nagar, who is a co-founder and the CEO of 374 Water, and Mark DeSuze, who is the CTO and co-founder of 374 Water as well. Mark or Kobe, do you just want to say a quick hello?
Hey guys, good afternoon. This is Kobe. Great to be here, and we're looking forward for your questions later.
Yeah. Hi everyone. I'm Mark DeSuze, and this is a great opportunity. So we're excited about sharing this information with you and engaging in a dialogue with you in the future.
Fantastic. Thank you, gentlemen. So we want to talk about inventing the future with us, with 374 Water and a paradigm shift in waste treatment. You know, we're moving from what we call treatment to resource recovery, and with the technology we're bringing to market, it's supercritical water oxidation. 374 Water is a social impact clean tech company based in Durham, North Carolina, and we're commercializing a novel approach to supercritical water oxidation that was invented by the founders Kobe Nagar and Mark DeSuze with the support of Bill and Melinda Gates Foundation, as well as a lot of fundamental research and investment done by Duke University as well. And our mission overall as a company is to support a clean and healthy environment to sustain life. And what you see at the bottom there are the sustainability development goals for 2030. And these are the specific goals that we believe this technology and the transformation it can bring to the waste management and wastewater and biosolids management world can help us accomplish these particular objectives. We really are, with this technology, talking about a shift in paradigm from waste treatment to resource recovery. And we know that, the waste treatment with incineration and other technologies has been talking about resource recovery for quite a while. But the shift we're talking about is fundamental, where we're looking at wastewater treatment plants as becoming water resource recovery plants, and the same thing with waste, and doing it in a way where we're truly transforming the waste into something that's useful and reusable, as well as eliminating contaminants and creating byproducts that have net positive value. So we see it, recover resources. It's also important to look at decentralized and modular treatment rather than creating these very large centralized units where we've got to pipe or transport all the materials to a centralized location. This is a modular, compact, and prefabricated approach where we can treat the waste at the source, where we're going to reduce volume 99%, destroy all the contaminants. We want these technologies to be energy efficient, self-sustaining, and resilient, and they need to integrate with current infrastructure. There's been billions and billions and billions of dollars spent in the water and wastewater industry and in industry itself, in manufacturing plants and wastewater treatment plants, where we're not just going to start over. We've got to be able to integrate these technologies into the current footprint. And we're also looking at transforming the materials processing. This idea behind decentralized resource recovery is also part of a circular economy where, we start with our raw materials, we start with our production, but then we move our wastes into a unit like you see a NIC 6 there, which is our unit, where then we're able to recover energy, minerals, distilled water, and bring those things back to produce clean fertilizer, to return clean water that can be reused. So the idea is, we're taking what we've used to create products to provide and then treat water that comes out of our houses and wastewater that comes out of our houses, and be able to recover and reuse those resources so that we are demanding less of new usage of new water and new resources from the environment itself. When you look at, and you all know this, when you look at the value of a barrel of fecal waste, this is obviously an undeveloped country where someone is pouring a 55-gallon drum of waste. We think of it as another way. You could look at it and say, that barrel has 87 kilowatts of energy in it, which is the same energy as a Tesla SP90. And that's one of the fundamental principles of what we're trying to do, is take advantage of that, the energy that's in that waste. Now, when we talk about biosolids management today, I think we all know, and one of the reasons I think we've generated some interest here is we know it's a wobbly three-legged stool. The regulators, with some of these emerging contaminants and where we're at in just these particular technologies and capabilities, landfills, incineration, land application are becoming more and more difficult, and there's starting to be some pushback on all of these, particularly when you start talking about emerging contaminants like PFAS, where it's very difficult using any of the conventional technologies out there to get it down to parts per trillion levels that are acceptable. The other side of it is, and this is a quote by Albert Einstein, is we can't solve our problems with the same mindset that created them. So continuing to bury things or applying them on the land or burning things, all we're doing is moving materials from one medium to another. We're not really destroying them, or we're not really recovering and reusing them, and that's where we need to get to. So SCWO, Supercritical Water Oxidation, offers a choice. And what I want to show is on the left, you see a landfill, you see land application, and an incinerator. Each one of those is leaving residuals somewhere on the land. What you just saw on the video there was the waste going in, and that's what comes out. That's it. There's no additional. There are some minerals which we're looking at to reuse for fertilizer and other use. There is that water which can be used, reused for many different things depending on the actual spec that you of the water that you want to use, or how you want to use that water. But that's it, and that's the beauty of this. The systems that we're talking about are compact. That's a 20-foot cargo trailer. The larger systems go on a 40-foot cargo trailer. But as we said, if you look on the right there, the black capsule, that's what's going in. On the right is the effluent that came out. With some of the cloudiness in the materials you see at the bottom are the minerals, the things that don't oxidize and transform. They drop out, and you wind up with the minerals. You wind up with water. And on the units The larger units were actually generating electricity, which can be used to sustain power for the unit, and you can also use the electricity elsewhere in your facility. And again, you can see Kobe over there on the right holding up an influent and effluent sample. Taking a look inside the units, we said they're compact and prefabricated. We've got a heat recovery unit, a reactor, slurry pump, gas and liquid separators. This is what we call a NIX-1, which treats roughly up to 1,000 waste from 1,000 people per day. When you look at the unit itself, it can be integrated very easily into an existing wastewater treatment plant. The unit plugs in essentially after your dewatering, if you're looking at it for biosolids and sludge treatment. And then you basically, when you're done, you have distilled water, you have minerals, and then whatever comes out of the filter and the watering. But it does fit into existing footprint. If you think of these 20 or 40 foot cargo trailers, that's the space it needs. And here's an example of a project that we've been working with Chapel Hill, where if you look, all the red X's are pointing to all the current sludge treatment methodologies that are existing and operating at this facility. If you were able to put in place three NIX 30 units, you can potentially replace these units and then recognize the savings in electricity, power, waste generation, and so forth from that. So you get an idea of when we talk about compact and modular and how it integrates into an existing site. It's pretty clear right here. Now what I want to do is step back away from the box itself and talk about the process of supercritical water oxidation and talk to you more about what happens in the box and what type of wastes we can accept and what happens to those wastes. So when we say supercritical water oxidation, what's happening is we are raising the temperature and pressure internal of the system and raising water to a supercritical phase where at that point it has a similar strength as acetone to dissolve organics. So you're able to dissolve the organics, and then you're putting in excess oxygen that is then able to oxidize the materials and essentially break them down into their fundamental carbon dioxide, water, and minerals. And that's it. So we're operating, if you don't know by now, 374 water. The 374 is 374 Celsius, which at that temperature and about 221 bar pressure or 3,200 psi is the temperature and pressure at which you reach that supercritical phase. When you look at the reaction itself, using some fun little icons there, we've got our waste and our poop. We like to say poop. As we know in this business, it's poop to other people, but it's our bread and butter. Little joke, right? That mixed with air at 374 degrees C and 221 bar produces clean water, some CO2, nitrogen, water vapor, heat, and then minerals. The heat is recovered and moved back up to heat the incoming air, and the excess heat in the larger units can be used for electricity. The beautiful thing about this is the reaction occurs in seconds, and we'll show you from a process view what this looks like. So you've got the ambient air coming in through a compressor, going through an economizer where it's being heated up and moving back to the front. You've got the wet waste on the top left coming in through the heat exchanger, heating up, and then it will start moving through the reactor, and then through the separator, and then you see it goes through the cooler, and then we get our water and minerals out. We also collect some distilled water off the expander, and then we have our vented gas that goes out. And again, this all occurs in a 20 or 40 foot cargo container. The reactor looks like a space heater, but it's actually a tubular reactor, and the reaction time is seconds that you move through there, and it's essentially mineralizing the waste. I'm going to take a pause here. Kobe, would you like to make any further comment about the process itself, or Mark about the chemistry and thermodynamics itself?
Hi, can you guys hear me?
Yes.
Great. This is Kobe. So we're talking about a completely new approach to waste, and what's important to realize is this is a full transformation of the waste that has been done using the energy of the waste. We don't need any other supplemental energy beside the waste itself.
Thank you, Kobe.
And it's a continuous process, so we get that question a lot.
Yeah, it is a continuous process. They're designed to operate continuously for a month, and then you have some routine maintenance around rotating parts, but it's intended to be running 24/7 with a continuous operation. The waste streams that we've tested and that Duke has tested on the NICS unit at the Duke University: dewatered secondary sludge, primary sludge, waste-activated sludge, food waste. We've also commingled these wastes together, and we've also looked at waste motor oil, vegetable oil, landfill leachate, plastics, industrial wastes, and we've also included in there our RO, reject water, and other types of waste that have been contaminated or that are contaminated currently with PFAS and other organics, such as drugs, aspirin, or other pharmaceuticals. So we've done a number of robust tests of individual waste streams, mixed and commingled waste streams. If you look at an example of primary sludge treatment, you had COD of 170,000, reduced 99.9% to 70 parts per million. You've seen VS, yeah? Question?
Nope.
We've seen the volatile solids reduction of greater than 99%. You can see the nitrogen removal 94%, phosphorus removal just about 96%. So significant reductions, and pH levels of around 6.6. When you look at the fate of nitrogen, phosphorus, and sulfur, the nitrogen essentially is transformed into nitrogen gas along with the CO2 and H2O. The organic, phosphates are generally phosphate precipitants, and then sulfur is, you've got sulfates, hydrates, and calcium sulfate that come out of this itself. And what we're looking at here, on the phosphates, is how can this potentially be reused for fertilizer? When you look at PFAS removal, we did a study with a small wastewater treatment plant in Maine, lime stabilized sludge that was contaminated. You can see there with 110,000 parts per trillion of PFOS. If you look on the right here, you'll see a table. We had 99.95% of PFAS removal, 99.98% removal of PFOS. And you can see down the board, everything was reduced to very, very low parts per trillion numbers, and in some cases, below detection limits. I'm going to stop there. Mark, did you want to add anything? I know you've done quite a bit of testing and looked a lot of the chemistry of the influent and effluent. Would you like to add anything at this point?
No, not really. I think what's remarkable is, as Doug is sharing a selection of results here, we have several years of research and demonstration with this pilot backing our results. We've done hundreds of runs, ran for over 1,000 of hours, and pretty much everything that we've fed to that unit has been treated and destroyed. And even the most recalcitrant compounds. And the example here is the PFAS. So no, go ahead, Doug.
Fantastic. Thank you, Mark. So when you look at this compared to conventional technologies, and I want to be very clear up front, these conventional technologies are sound, they're proven, they continue to be improved upon. The technology and the innovation curve continues with these. But what we want to bring out today is that there is now a choice to move from conventional technology to advanced and future technologies. So if you look at this in terms of effectiveness, in this case, we've got our little friend there, Peter Poop. The effectiveness in incineration is probably the same, but when you look at it from the emerging contaminant, particularly like PFAS and others, you'll see that probably drops down to a single Peter for incineration, where SCWO is looking to be 3 Peters, Peter Poop. And the reason I say that with some confidence is there's been a recent press release and recent information out from studies that have been done with incineration in New Jersey, where they basically stopped the testing because they just weren't seeing the results with the PFAS removal that they were looking for. From a CapEx standpoint, SCWO is competitive with anaerobic digestion and more competitive on the incineration. OpEx is very, very low. particularly in the larger units where you have self-sustaining energy circulation. The footprint, significantly less than anaerobic digestion and much smaller than incineration. Energy consumption, we actually create energy in the larger units. Polluting emissions, we don't really create any at all. And then from a sustainability standpoint, what we talked about there is being able to continue to sustain itself over a long period of time. We believe that the SCWO is superior there as well. Kobe, this is your slide. If you don't mind, I'm going to ask you to give a little history. Now, SCWO has been around, and some of you that have been in the industry for a while will know that SCWO has been around and been looked at for about 25 to 30 years. I myself, how I came to meet up with Mark and Kobe is when I was with a pharmaceutical company 30 years ago. We were building a new facility in South Carolina, and we were looking at supercritical water oxidation because it was going to be a research and development facility, and we knew we were going to have active pharmaceutical ingredients and other refractory and recalcitrant molecules in our wastewater. So we were looking at supercritical water oxidation to essentially be a point source resource recovery and treatment unit. However, at the time, the technology just didn't lend itself to a maturity where it could be run extensively and continuously without very, very high operating expenses. When I met Kobe and Mark and started to look at 374 and the work that they've done with Duke, they've really overcome a lot of that. So Kobe, if you don't mind, I'll let you compare a little bit to what's been around the market before and what makes this different and why we think it is unique and offers the market a whole new way of addressing the waste problem.
Yeah, absolutely. So I like to say that we're standing on the shoulders of giants because the technology was developed back in the late 80s to treat ammunition and chemical warfare, and there was a lot of work that was done in that field. What worked for our advantage is we started this exploration in an academic institution. So that means that we had access to all of those cases, and the way that we're seeing the land of supercritical, there are actually two groups or two thoughts in that area. So several groups were focusing on treatment with pure oxygen, and the second group of people were actually looking on a single stream. What we call bringing the waste from ambient to supercritical in one single phase, single stream. And we looked on all of those cases. We picked what worked and what didn't work from them, and that's the way that we were able to innovate and move the technology further into where we are today. So we actually have created a hybrid between those two systems, using air, which is much safer, but also using the multi-stream approach that allows us to react very effectively with low energy requirements. Yeah, Doug, if you can click one more, so we'll get our missile going.
Is that what you wanted to see, Kobe?
Yeah, exactly. And there was a question on the Zimpro and how we're different from that. So maybe Mark can talk about that for a second.
Yeah, sorry for the delay. Somehow the unmute button is kind of slow on this Friday. Yeah, I think it's clear that there are a number of technologies that historically have been around, as is shown on this diagram. And Kobe just mentioned Zimpro, which is a high temperature but subcritical treatment that was very, very promising in terms of its ability to handle biosolids. But really the issue is the untreated fraction or the residues, which are really nasty and contains a bunch of phenols. And also the fact that Zimpro smells really, really bad. By bringing the temperature up one notch and working under supercritical conditions, as we do. You saw the slides. You saw that the effluent is of very clean water, and that can be discharged. Back to you, Kobe.
Zimpro is the technology that I was looking at 25, 30 years ago, and that's when Zimpro first started looking at it. And again, we looked at it as, you know, some of the issues that they had were, you know, corrosivity, clogging, the hazard around dealing with pure oxygen. And there are, in the patent pending process that's been created, you know, through the work of Duke and Mark and Kobe, and through the work of Duke, they've come up with some unique aspects of the design that eliminate the clogging issues. The materials of construction have overcome any of the corrosivity issues that you're seeing in normal operations with the SCWO unit. And because we're using compressed air for the source of oxygen, we've eliminated the process safety hazards around handling pure oxygen, as well as the operating cost of having to, you know, continually feed oxygen. So the expenses associated with the unit are really just electricity, standard, you know, maintenance, you know, and that's it. Kobe, did you want to say anything more before we move on?
No, you know, we can answer some of the questions now, or we can save it later. But
yeah, let's open up to questions now. You know, one of the things we wanted to do is leave plenty of time for questions. So why don't we do that?
Sure. There was one earlier that was basically related to how you would scale this up. So the question was whether you would need a farm of 40 of these units for a treatment facility that services about 50 or 60,000 folks and generates 1,100 dry metric tons of biosolids per year after digestion.
Kobe, do you mind taking that one? Yeah, absolutely. So that's a great question. So regarding to the 1,100 tons per day, that's actually slightly lower than what the mixed 30 unit can treat. So as Doug mentioned, we have a NIC 6 that is designed for 6,000 people, and a NIC 30 that is designed for 30,000 people. You know, post digestion, that number of people is actually growing. So in terms of tons, we're talking about 1,200 dry tons per day for the NIC 30. So you only need one system, and it's a 3 40-foot containers.
Other questions?
I think there was one question on the temperature in PSI and Fahrenheit. So 374 degrees C is 705 degrees Fahrenheit, and we operate above 3,200 PSI. So in terms of pressure and temperature, it's slightly above a diesel engine.
While you guys have this up here, there was a question about the makeup of the gaseous emissions, the vented gas and air emissions. Can you talk about what those contain other than NOx and other traditional pollutants?
Yeah. So the interesting thing is it doesn't contain NOx, actually, because the temperatures are low enough for not having NOx formation. So all the organics go to CO2. So we have CO2 in the effluent. Actually, the nitrogen gets transformed into nitrogen gas. So the effluent is very clean. We have not measured, we have measured, we've looked for SOx, and we don't measure any. And so in terms of gaseous effluents, it's a very clean effluent.
Yeah, we NOx your SOx, basically. So
that's why the reactors are called NIX reactors, because there's we're nixing everything.
Other questions? So there are more questions. Yeah, they are. And I'm having a little trouble keeping up. So if Kobe or you see any that you can snag from the list while I'm reviewing.
Yeah,
there was a question about the status of the commercial scale up of these?
So right now we're designing and building our NIC 6 units, and those will be available next year to purchase. The next product will be the NIC 30.
Yeah, and I see
Doug,
two questions I can address here in the chat regarding what happens to PFAS when it is treated. We actually destroy the PFAS. We break the carbon-fluorine bonds, and the fluorine atoms end up as fluoride in the liquid. Partly related to the end product, the question is, can nitrogen be recovered easily for sale to a company? And nitrogen from that effluent would not be particularly relevant because air is 80% nitrogen. But if you're in the nitrogen business, you'd be just looking at air. However, CO2 can be recovered in a concentrated stream by some slight process modifications that we've put down in our innovation to be done down the road, and that could be solved. We joke about the fact that we treat biosolids and that we could do carbonated beverage with the CO2 coming out. So allow me that little joke on a Friday.
Yeah, I think we skip one question about the electricity produced. So the NIC 30 is producing enough electricity to power all of its auxiliary plus a surplus. The smaller unit, the NIC 6, still consumes.
Kobe, here's the slide that shows it.
That's great. So maybe you can talk about that for a second.
Yeah. So the next one is the Duke Pilot, and it has a loss of 20 kilowatts. If you look at the NIC 6, which is the next unit size up, there's a 10 kilowatt requirement per. And then when you get to the NIC 30 and the NIC 200, that's where you start having a net positive creation of energy that then can be reused. I don't know if you want to add more to that, Kobe, or not, but the split is between the NIC 6 and the NIC 30.
Yeah, the only thing that the numbers, the tons per day, are wet tons per day.
Okay, let's look at some more questions. We got lots of great questions. That's why we wanted to go through this. We weren't rushing, but
no, and I appreciate you helping me try to moderate some of these questions. They are really good.
I can see, one question on the waste usage. So what we're looking for is using the minerals that we get at the back end as a fertilizer. We did a study with NC State looking at that compared to industrial grade fertilizer, and as is, they're doing pretty good, almost 90% compared to industrial grade fertilizer. And those are clean. Those don't have any contaminants on them.
So here's a really, really good, this is a question that kind of parallels one that was asked earlier. Kobe, this is too. If you're using multiple units, are they being used in parallel or in series?
They're using in parallel.
Great. And then there's two questions about the temperature and pressure. First one is 32 PSI requires very special high pressure pumps to get the solids into the reactor. What are the energy cost, maintenance issues, and safety concerns? And the second question, which is related, is what's the operational risk with the high temperature and pressure, and what are the safety concerns? So same thing, talking about the robustness of the materials, the equipment for the high temperature and pressure, and then the safety associated with that. Kobe or Mark, do you want to touch on that?
So I can touch on that. So safety is obviously the number one concern from our perspective. We have the unit on the Duke campus operating from 2015 with knock on wood zero incidents. Where we are operating is at high pressure, but the most important thing to remember is the amount of volume that is that's being held by the system. And that's the beauty of the technology. It's allow you to react a really high throughput in a very small reactor. So in terms of size, the reactor size is actually a 1 liter, and that can process about 1 ton per day. So that actually reduced the amount of risk, and everything is being contained inside a container. And of course, we have the safety layers around that with a control system and some passive energy release system.
Great. There's a question about the range of solids, 10 to 16%. Correct, Mark? That's the optimum range.
Yeah, and because we can only handle so many questions, I started to answer some of the questions in the chat because some of them are really quick answers. Really, we for energy efficiency and self-sufficiency, having something around 15% dry solids content is ideal. We can obviously handle stuff that has more. When it has a lower calorific content or lower solids content, we can supplement with a little bit of extra trim fuel. And we've used different things such as waste oil, food waste, fat, oil, and grease. Related to that, there was a question about landfill leachate. We have treated landfill leachate quite effectively. And that stuff is nasty. It smells and it has a bunch of horrible things. Typically, landfill leachates, except for those landfills that are elevated temperatures that tend to have COD in the range of 30 to 50 grams per liter. Typically, landfill leachates will need extra fuel added to it. At Duke, we are going to start looking at synergisms at a landfill to feed things that otherwise would go into the landfill. So kind of a double whammy there. But yes, landfill leachate is definitely a very great application for that technology as well.
Mark, what about there's a question about heavy metals concentration. Heavy metals are naturally occurring.
Yes.
So if you take away the carbonaceous material, obviously you're concentrating it. Have you looked at the chemistry of what's left over in the solids and the heavy metals?
Yep. We so obviously metals in equals metals out. Whatever enters the unit must come out in some form, and typically we precipitate a lot of the metals in with the solids that come out, and we have characterized that. We haven't done typical TCLP to see how leachable they are. That could be a focus in the future. Typically, when we work with biosolids, the metals concentrations tend to be low, but it wouldn't have to be looked on a case-by-case basis.
Yeah, there's one question here about special materials of construction. I want to go back and make sure everyone's clear. The units that we showed earlier, the NIC 6, and up from there, these are prefabricated units. So everything inside the box and some of the material handling equipment and things that go outside the box are standard. This is a standard bill of lading, standard design. The only thing that's going to be different is your integration on your site, how where you put it, how you do the hookups. So that's one of the things we're also looking at with this paradigm shift is being able to mass produce these units and very quickly deploy them in a very small space and in a very consistent way. If that wasn't clear before, I want to make sure. So as the comment about materials of construction, all the materials of construction, all the pumps and the hardware and everything is going to be basic, is going to be preset and predetermined and designed in to the unit itself. The only thing that happens that's unique when it's installed is we may be able to do some tuning based on what your actual streams are, some fine tuning of an optimization of the unit. But there is no customization. This isn't a custom design and build from a treatment unit, operation unit process. The only quote unquote custom design and build has to be done is the integration of the unit into your site itself.
Doug, I want to take this question number 43, and then we'll maybe go on with so
Oh, good. That's a good one. Yeah, please answer.
Yeah. So the comment is a very good one. So you need actually high organic content, is anaerobically digested biosolids to low strength. This is very interesting. So digested biosolids are stabilized. And what that means is that the BOD gets low, but the COD is still relatively high. It has a slightly lower calorific value than undigested biosolids, but it's still very combustible in some sense. It has plenty of calorific value, and you can treat it very well by supercritical water oxidation in our units. So it is perfectly fit for that.
And just to add to that,
to Doug to I think go through the remaining slides maybe.
Yeah, that'd be great.
Yeah, there's some questions about economics. So let me do this, and I'll let Kobe. If you take a look at our product sheet, you can see the NICS 6, NICS 30, and NICS 20. So Kobe, do you want to talk to the different units and maybe a little bit to the economics?
Yeah, so obviously, you know, bigger system have better economics, some economics of scale. Where we see the application is the decentralized approach. You know, the fact that we are mass producing our units actually create a really good pricing point in terms of capex. I think we didn't mention OpEx, but OpEx is very low. It's only the maintenance for the rotating equipment, because you don't need to use any chemicals or electricity to run the process. And we also generate, you know, valuable stream down, like distilled water that can be used for cooling towers or boilers, chillers, and the solids that can be used as a fertilizer.
Great, thank you. So
one added to the percent solid. Actually, our base case is based on a digested sludge. That's where the 15% comes from. If we treat in primary sludge or food waste, that solid percentage is actually can be lower because they have more energy embedded in the waste.
Thank you, Kobe. So we are engaged. We have quite a few external engagements going. We've done some presentation work with LIFT. Obviously, we've been working with Duke. At NC State, we've been working with as well. We've done Blue Tech research. We did an innovation. We're going to be we're a sponsor at WEFTech. We are doing some work with the EPA PFAS task force. And we're also talking with New Jersey Department of Environmental Protection. They've got a number of initiatives around environmental justice, climate risk, pollution control, you know, and PFAS as well. And then we've been participating with the Department of Energy, who is looking at, you know, this moving wastewater treatment to water resource recovery. We had won a prize there, one of 10 others that we won a prize for the initial concept and innovation that we're providing. And now we're working on a phase 2, which could lead to a demonstration project with a municipality or another private entity. You know, from a summary standpoint, it does work. Treats biosolids greater than 99.9, destroys pathogens, emerging contaminants. You know, you saw greater than 99.9 in most cases. Generates clean water, produces energy, and there are some minerals that could be recovered and reused. And it's competitive at $25 to $60 per wet ton, especially when you start thinking about the disposal costs, the off-site transportation, and the disposal costs. And then as you start to get into what we might see in the regulatory prohibitions, there may be no choice but to find another alternative. The call to action that we're at right now is we are looking to work with entities on demonstration products, and we approach these with 2 tasks. The first one is we can do a treatability demonstration at Duke using the Duke NICS 1 reactor. We work with you to identify an appropriate waste stream. You ship it to Duke. We treat and demonstrate effective treatment. You're welcome to come to the site and witness a demo. And then we do a review where we'll look at the analytical results and go through and review that with you. If what we're seeing so far, folks are satisfied with that, then we can move to a demonstration at your location where we can identify, your most challenging waste stream, integrate and deploy a NICS system on location, conduct a 1-month qualification and do a go, no-go to permanently deploy it. The time frame for doing task 1 is 2 to 3 weeks. Then the what I call in project management, the long pole is really just the logistics. And the second on the demonstration, it's going to require, it's probably a longer period of time. We're looking at, having demonstration units now in mid to second to third quarter of next year. So we're looking to pre-qualify and determine, where we can put those NICS 6 or more NICS 6 units. And we are accepting orders for folks that, want to go really start looking and are interested in this and putting a system on their site. So that's our call to action. So if you have interest, you can get our contact information from Janine. And we also have info@374water.com, and there is our website. My contact information is at the lower left. If you want to write that down, you can contact us. We'd love to hear from you. We also have a presence on LinkedIn and Twitter, so please do follow us. And at this point, that's the end of the formal presentation. Janine will have a PDF version of these slides, and we're also going to provide a case study that we presented to Blue Tech, which is the lime stabilized sludge. So that's a 1-page. We'll also have that for you. And anyone who's going to be attending WEFTEC, you'll be able to see we have an exhibitor page with a couple of videos, and will be available during WEFTEC. Thank you all. Is there any other last-minute questions?
So, Doug, what I think I will do is cut and paste the chat so we make sure that you answered all the questions. And if you didn't, we can certainly include those answers in the follow-up. But, yeah, thank you, Mark, for kind of answering as we went along. This has been the most questions we've ever gotten on a Lunch and Learn. And I was getting a little overwhelmed there. But so, yeah, I think unless there's any other questions, Mark or Kobe, that you picked up that didn't get answered.
I think one of the questions that I saw was higher strength equal higher cost. Not really. So higher strength stream actually sometimes better for the economics if they have the right calorific value. And we can do a case study if there is a specific case we need to look at. I think what's important to understand is our system can work upstream or downstream a digester if you have one on your site. And we can show that we have shutdown economics for the digester once you feel comfortable with the technology. But the starting point can be just offsetting landfill cost.
Yeah, there's another application we see too within a service area is if you have a lot of industrial pretreatment customers, if you've got some that have particularly high organic streams that have historically caused problems, we could actually go into an industrial facility and put in one of these units to basically, render their effluent, put this in as a pretreatment unit, render their effluent, as high quality water, with maybe some solids. So that's something else. And we are talking with several industries out there and several, in the waste industry as well as in some of the heavier organic manufacturing, where there's been some challenges in making sure that there's nothing released that's going to cause pass-through or upset at a publicly owned wastewater treatment facility. So with that, I'll ask one last question. If anyone wants to roll their dice and pop up in the chat and let us know whether you're interested or not in further conversation. Give you a minute to do that, and then we'll wrap up, Janine, and turn it back over to you to close out the presentation. So we have anybody specifically that wants to say, hey, we want to talk? Of course, I had to ask.
And some of that may come after the fact.
I know everybody's shy. But, and for those of you who may have been offended by not using the proper industry terms, instead using poop, I apologize in advance, and we'll make sure to be careful not to use that in the future if if folks in the industry feel that it kind of sets the value a little bit lower than what we do and how we look at everything we do. So thank you all again. We appreciate your time and your interest, and we look forward to hopefully talking to you in the future.
Well, we definitely want to thank you guys. It does seem to be a promising technology, and we're all rooting for you. Best of luck. And thanks again to everyone for joining us today. We're always looking for suggestions for future sessions, so please email me if there's something you'd like to learn about at your Lunch and Learn. And again, I'll be following up with the recording, the slide deck, a case study, and answers to any other questions that you did not get answered today.
Thank you, Janine.
Thank you, guys.
You're
welcome.
And have a terrific weekend, everyone.
Bye-bye.
Bye. Thank you.